Yeah, okay. My audio is working. Sorry for the late start. I had some technical difficulties and work went a little bit long today. Get all my little details worked out. Cool. Okay. So, for now, let's fix this here as well. Cool. I still got a cough. I'm trying to get over it though. I think today we will do a couple of things, plus whatever requests I get. First thing we're going to do, I think, is a utility function for a lot of robotics projects, because robots, in general, are tank drive, so they have a wheel on the right and a wheel on the left, and you have to be able to control them. And if you want to be able to steer the thing, you need to be able to, tell it which direction you want to go. And with remote-controlled robot-like things, it's common to control it with a joystick. So a single joystick has an X and a Y. Hey, thanks for joining. If you got questions, feel free to pop them in the chat. Otherwise, we're just going to talk about some robot stuff. Anyway, so if you have a joystick and you want to control a motor, then you have, something with a y-axis and an x-axis, and you have a joystick with a point that you can put, anywhere you like in here. So see, right, left, forward, backward, some combination thereof, and you want it to be able to control the motors on the robot. So if you have you've got right and left that can spin forward, backward, and you want to turn the joystick into tank drive. You need to be able to convert between those two. Specifically from one to the other. And so we can do that. It just involves a little bit of math. So if we call this X and this Y, and this point is at X, Y, we can start to do some things. Because this, if I can draw it, looks like a vector. And so that vector is just X, Y. So the angle equals the arctangent of y over x. But in programming, we have the option to use a function called atan2, which is arctangent. If I can spell arctangent with two arguments, and we'll put it in y, x. And so that'll return our angle with all of the signs working out nicely. The other thing we can find is the magnitude. So we'll call that L. Sure. And that will be x, or the square root of x squared plus y squared. Which we have from the Pythagorean theorem. So the longer this vector is, the further away it is from the middle, the faster we want the robot to go. And we want its speed to behave in the direction that we told it to via the joystick. So we want it to be speed at angle. And we need to be able to control right and left motors appropriately. So if we, no, I better not use L here because we were using L for the left. We'll call it V for velocity. So we have left is equal to something, right is equal to something, and we want speed to control both of them. And speed is probably going to multiply something. And the last bit, we know left and right should behave similarly, but when the angle changes, or when we're trying to go right or left, we want one to behave opposite of the other. So one of these will probably have a plus, and one of these will have a minus. And I don't know if I put those in the correct places yet, but we'll get there. So something that I notice as I'm looking at this is this part, which is the cosine theta part, is going to increase as I move it to the right. So as I push it more towards the x, as if I'm going to turn right, that number goes up. And if I'm trying to turn right, I want my left motor to move faster and my right motor to move slower. So let's say this part is cosine theta. And if I do that, here I have plus, here I have minus, then if I try and move it straight right, then I have whatever this quantity is. We'll put zeros for now because we haven't decided what goes there. We'll have cosine theta goes positive as I push it right. So this number goes up, left moves forward. So forward is plus, backward is minus. And then on the right-hand side, this motor should be going backwards if we're pushing straight right. So this negative cosine theta becomes negative, which is exactly what we want. So that's good. But if we push it straight forward, right now we don't have anything in there that will make it do anything when it's pushed straight forward, because the cosine of 90 degrees is 0. So now we need another term that's going to control our front to back speed. And since we want forward backward to be the same on both motors, if we're pushing straight forward or straight backward, this term is going to probably be the same. And in fact it is, because this part, sine theta, is related to the sine of the angle. And so sine of theta goes here. So if we ignore this cosine portion for a second, we're saying we're moving it straight forward and backward, so this part's going to be 0 anyway. And the sine of 90 degrees is 1, so it's v times 1. So it's just however far we're pushing it times straight forward, which is going to make both of them move forward or backward together. Is that right? Yeah, because if I push it backward, then the sine of negative 90 is negative 1. And so it'll go backwards. So ultimately, if we have joystick in, so I'll use Python syntax for now, def joy to tank of x, y. Then we're going to have theta, and I would write out, my variable name would be theta, not the theta symbol, but for the sake of simplicity here, theta equals numpy, or whatever math library you're using, dot arc tan 2 of y x. Is that correct? Yes. And v equals np dot squirt of x to the 2 plus y to the 2. And then L is just v times sine theta. So again, it'll be your math library. np dot sine of theta plus np dot cosine of theta. R equals v times np dot sine of theta minus np dot cosine theta. Return left and right. And that function will convert a joystick signal into an XY, or into a left-right motor control signal, which is lovely and very useful in robotic stuff. So that was a robot thing that I wanted to cover, mostly because I have robotics kids who will probably end up using that at some point in the near future. So, if we move on to the Mandelbrot stuff, I don't have any requests yet. You may or may not be familiar with the Mandelbrot. Let me see if I can find... I don't know why this is in French. Or whatever this language is. No, not Mandelbrot.com. You've probably seen the Mandelbrot before, which is a member of the larger set of these fractals called the Julia set. I am not an expert in any of these, but the Mandelbrot is a very fun way to experiment with graphics libraries and stuff. So if we come here and look at the Mandelbrot set, we can see some of the math, wherever it is. Where's the Mandelbrot fractal? Maybe that's what I'm looking for, is the fractal. Hello? Back button does not work. Wiki, it's the same page. I just want the formula. It relates to the complex plane. So, if I can find it. Maybe it is here. And I just missed it. Formal definition. Why is this formula so tiny? Still tiny. Like relates to the complex plane. So if we have a number here, let's say a number C, if this is the imaginary axis and this is the real axis, come back here. Set a value c in the complex plane for which the orbit of 0 under iteration of the quadratic map z(n squared plus c) remains bounded. So if you start with z naught equals 0, z naught equals 0, and then you have your arbitrary zn is equal zn plus 1. So when we're trying to find the next one in the sequence, we take the current one, zn, square it, and add c. Which is really not that hard to do. So if that's 0, 0, suppose maybe c is equal to -1 plus 1i. Now I'm fairly certain that this is not going to converge, because realistically speaking, you got to be really close for it to actually converge. But the way they get the gradient is they measure how fast it does or doesn't converge, which is kind of nifty. So if we take c, for example, we'll say yeah, so this will be our z naught column, or our zn column, and this will be our n. 0, 1, 2, 3. We're not going to do a ton of them because they take a while. But for z naught, we've got 0. For z1, we're going to take z1 equals 0 squared plus c, which is 0 squared plus -1 plus 1i, which is equal to -1 plus 1i. -1 plus 1i. And for z2, we will now take this value and feed it in here. So then we have -1 plus 1i squared plus -1 plus 1i. And if we distribute, we get -1 times -1 is +1. And we'll get minus 2i plus 1i squared, we'll expand that in a second, plus -1 minus 1i, plus 1i, equals 1 minus 2i, and this I squared turns into -1 minus 1, and then breaking into this one, we have -1 plus I, equals 1 minus 1 is 0, minus 1 is -1, -2i plus I is -i, so -1 minus I now we'll do z3, and we may do 4. So z3, we will now take this -1 minus I squared, and then add -1 plus I. And then when we square it, we get -1 squared is 1, -I, let's see, this one I have to do 1 plus I. And then we have 1. And that's going to be plus 2I minus, nope, plus I squared. 2I plus I squared. And then we add to that this negative 1 plus I. So then we have this that we can combine together. So we'll just get rid of these parentheses because we don't need those anymore. So 1 minus 1 is 0. I squared is negative 1. 2I plus I is 3I. Did I do everything correctly here? Yes. Yes. And so that's negative 1 plus 3I. Now, there is a convergence criteria that has been proven by somebody else, and I'm not going to prove it here. But the convergence criteria is that if the value exceeds 2, yes, or if the magnitude of z is greater than 2, it does not converge. So we can actually take the magnitude of this number. So the magnitude of z3 is equal to negative 1 squared plus 3 squared. Actually, square rooted. So then you have the square root of 1 plus 9 equals the square root of 10, which is greater than the square root of 9, which is equal to 3. So it's greater than 3, which is greater than 2. So c equal negative 1 plus I is not an element of the Mandelbrot. And I'm just using the scripty m for that. So negative 1 plus 3i. So that point's not in there. And we could, if we wanted to take the time, go through all of these different points, not all of them, but a subset of the point in the complex plane, evaluate this, and plot them. And if we really wanted to, we could see how long it took for it to diverge. And that divergence time we can set to a color. And while we could do that manually, I would I would much rather not. I would much rather make a computer do it. So what I'm going to do is switch our view so that we can see code. There we go. So now, this was just some test stuff that I did a little bit to make sure that my plane thing was working. So now what we're going to do is I have this thing that lets me create a Cartesian plane. And then I have a flag up here that lets me set it to complex. So we'll do this. We'll say complex equals true. So now it's going to be a complex plane. And this stuff that I don't need anymore. Hang on. Nothing should change for you. Good. I'll actually run this so that you can see what I did before. Hang on. That is not the right thing. Yeah, so this is just me fiddling around playing with a complex plane math, or with a Cartesian plane. So now if I do this, I'm gonna comment all of that, condense it. What? I'm confused. Why is it not doing the thing? This. I don't know what's going on. That, I'm done with all of this. Just hide. Go away. Okay. Bloop. That took too much effort. Okay, so I'm going to generate a graph of -3 to 3 on the x. I'm actually going to change that. I want from -2 to 2. Actually, I'm going to change that to 1.5. And I want it to be a square grid. So I'm going to say this is going to be from -2 to 1.5 is 3.5. -3.5 over 2. 3.5 over 2. Expected an int, got a float. Nah, you're fine. I'm sorry, I'm coughing all over the place today. So now this will give us... did I actually use this? No, I did not. If self.complex self.y equals self.y times 1j. There we go. That will make it complex. Now, yep. What I'm going to do is I'm going to evaluate that expression. So, for I in, yeah, for now. For iteration in range, we'll say 100 to 100 iterations. Actually, we'll say do 255 iterations. For reasons that we'll see in a minute. And then we're going to say image equals zeros in the same shape as our plane. And we're going to do plane So what I've done here is I've overwritten this class that I've made because I don't need the class anymore. It's just a constructor for my plane. And then I added the real part and the imaginary part so that I have a grid of complex numbers. So then plane, or I'll create another one called z equals np dot zeros in the shape of image. So z, that's z naught, and then the new z is going to be equal to z squared plus plane. And that's going to evaluate for all of the points in my complex plane. So it's equivalent to doing plus C. And now, image is going to be equal to Z image plus Z greater than 2. And so Z greater than 2 is going to give me an array of the same shape as my plane, but it's going to return true wherever that expression is true, and false anywhere it's false. A true, when I try and add it to something, will be will evaluate as a 1, and a false will evaluate as a 0. D-type equals. Telling that to be an integer because I want it to be an integer and not a float, because we're going to try and display it here in a little bit. And I think that's enough to do very naive Mandelbrot fractal. So now I'll do cv.imshow image, and we'll call it Mandelbrot. cv dot wait key. I have an error. Maximum supported dimension for an ND array is 350. Whoops. Invalid value. Oh, that's because I have to take the magnitude of Z. So np dot abs. I think that works. Nope. np. So I'll do np dot linalg dot norm Z greater than 2. That also does not work. What is axis equals, wait, that's why. Okay, Z dot np dot real of Z squared plus np dot imaginary of Z squared, and we're going to square root that. And if that is greater than, why are you complaining? Okay. Temp equals that. Print temp dot shape temp dot dtype temp dot min and temp dot max. Okay, 350 by 350 bool. Ah. Image plus equal plus temp dot as type np dot uint 8. Does that work? No. Why are you still whining? this up and unhide it. False, true. Okay. Okay, zeros and ones, that's good. Okay, print image dot shape, image dot d type, image dot min, image dot max. 15. Why is it doing that? Invalid value in square. Interesting. Seven, 8, 9. Okay. Okay, so I think what's happening here is we might need to add some protection. Well, first, let's do image equals image divided by np.max image. Just so that we can see a pretty picture. And voila! Can you see that? Is that showing up for you? Yes, it is. Very good. We have a Mandelbrot fractal. Let's make it bigger so that you can actually see it, because it looks fine on my screen. And let's take out those print statements that are slowing everything down. Boom. Big old fractal. So we can kind of start to see, you know, some of the weird stuff that happens out here, which is kind of cool. So let's attempt to optimize this a little bit, because it still takes it a second to run. If we have a number that's bigger than 2, we don't need to do this check anymore. Or we can at least speed it up by not having complex numbers in it. So anywhere this expression evaluates to true, we will replace it with zeros. Can we do that? Yeah. I think that'll work. Z equals Z times temp. True minus temp. I don't know if that'll work or not. Nope. Will that work? Looks like it. Yeah, totally worked. Exactly backwards to kind of what I was going for. come down here. Try this again. There are other things that we can do to optimize this, namely not use complex numbers. It just works out nicer for me right now. So 0 and 255. Very good. Now then, let's make it smoother, because if you saw, it's still kind of chunky. It's got lines in it. So what we're going to do... Actually, have I done better than that? I don't even remember at this point. It's been a while. No, I have not. Cool. So never mind that whole optimizing thing. That I have done here as far as getting the chunkiness down. I have done just as much here as I have anywhere else. Which is fun, I guess. But we can start to smooth out, or we can make the colors look nicer. Yeah. So now that we have the image here, we can apply a lookup table. Can we do that? I believe we can do that. Yes, we can. So what I'm going to do is I'm going to say for I in range 255. So I'm going to go through all the possible color combinations. And I'm going to create a dictionary. So lookup table equals an empty dictionary. For I in range 255, lookup table I equals, and we're going to create a value based off that. Should we do that? I want to experiment with something else first. Before we do that. So let's get rid of this momentarily. And I'm going to change this also temporarily. While max image is less than 255. Then do that. So this should be functionally the same, and we'll verify that. Are you gonna? It's taking its sweet time. This is why that OR thing is better. Thanks for the update. I'm starting to think I have an infinite loop somewhere. Yep. What? Magnitude of that's greater than 2. Take the temp as type. Okay. True or temp. What? Confused. Why this is not working? Okay. So square it, add the number, temp equals the magnitude greater than 2. So anywhere the magnitude is greater than 2, we will add it here. Okay. Temp greater than 2. Temp.max. I changed that. Why? What? Whoops. Helps if I put it in the right place. Temp.max. Not a number. Why are we getting not a number? Oh. It's because it doesn't converge. Okay. Try that. Oh. So bitwise or times 2. Yes. There we go. That is odd. It shrunk. Wow. Oh. That is why it shrunk. Does this work? I'm experimenting at this point because I've never done what I'm attempting to do here. Nope, that's not how that works. Okay, well, for now. Because what I'm trying to do is I'm trying to make the red, green, and blue channels correspond to the magnitudes of the real, imaginary, and magnitude parts, respectively. Just to see what happens, because I think it could be cool to see how those different channels interact. But I've not done that here before. Out of curiosity. print real np dot real of z dot max np dot imaginary of z dot max. Numbers stay around that. They stay around that because this guy helps. If I change that to a 4. Stop. So now you can see we're starting to get more details in there, and I think that's because I'm raising this limit. Well, I know that's because I'm raising the limit. So, if that's the case, let's stop printing that because that slows everything down. Let's change that to 1,000. What? Not 2,000, 1,000. And I guess that's fine. This is an experiment too. I've not done it, or I've not fiddled with that part. At least not that I recall. Probably doesn't help that I keep starting it over, but I'm curious and I want to see how it's progressing. Other thing that we can do here is use a library called CuPy, which will push this math off to my GPU. And I think I could do that fairly easily. Assuming I have CuPy installed. I can't remember if I do or not. Oh, look. Yeah. Yeah, so that's... Yep, that's how this is working. Okay. Well. Do I want to do that? Let me see if I have CuPy installed. That's a pretty picture, by the way. Import CuPy as CP. Nope, don't have it installed. I'll have to do that another time. Okay. So we have that. Maybe I'll do convergence and the imaginary and real parts of things. That'll work, right? If the temp is greater than that, it's going to generate a true, but I want the opposite, so this will do the opposite. Yeah, that's right. So everything in the Mandelbrot set is black in our images. And everything that is not in the Mandelbrot set is a different color. It's a shade of gray. So let's experiment a little bit. So we're having a problem where the imaginary parts and the real parts are both exploding and getting very, very large very, very quickly. So maybe something that we can do is take the log of the value if it's greater than we'll take the log of the magnitude value if the value is greater than if it satisfies this condition. That'll work. Can we do that actually? Yeah. So what we'll have to do is create a unit. We'll have to turn whatever vector into a unit length, not a complex number. Take a log of the magnitude and then multiply it. Does that work? Because convergence is contingent on being less than 4. Is it 4? Let's check. Nope, 2. Okay. Where'd you go? Here you are. Math. There we go. And I might be able to do that and see how that affects it. Oh. Interesting. Okay. Okay, so here's a thing. The reason we're getting some of those weird color things is the number is wrapping past 255. So if I just let this be any number, and then before I show it, print image.max, because I'm curious, but then set image equal to image divided by image.max. So it's not wrapping. I am genuinely confused. It's cool. I'm not complaining, but I'm a little weirded out because I don't know why it's doing what it's doing. Also, another thing that's a little interesting is this big gray circle, I believe, is a circle, and it's a circle centered about 0, 0 with radius 2. Just kind of fun. It sits inside the this Mandelbrot sits inside the not the unit circle, but the circle of radius 2. Fight. That's curious. Curious indeed. Can I set that to a 5,000? And it do something different? Now I'm just fiddling because I'm not sure what the effect of playing with that number is. It diverges more quickly, so it doesn't have to do as many iterations, which makes sense. And yes, if I wanted to, I could put a box around a particular spot on here. I just haven't. So, np.real. So let's take a look and see what the real part of z is doing. np.imaginary of z.max. Just to see what's going on here. Oh, that exploded. Still very large. Yeah, so here's what we'll do. Image, I'll change this. So we'll do plane dot shape 0 by plane dot shape 1. So that gets me the same width and height. And I'll do it by 3 channels, so it's color image. And we'll change this to be plane dot shape. And over here we'll say all of image channel 0. So this will be blue, green, red. So the blue channel will be the total magnitude. This one will be real, so this will be green. So the real part squared, and this will be the green channel. Zero, 1, 2. So this will be the red channel. 2. The imaginary part of z squared greater than 2 dot as type. And I should not. Yes, I should. As type np dot int. Doesn't have to be a uint 8 anymore. Let's just see what happens. Oh, shape ep. What do you mean it has no shape ep? Well, I guess it doesn't have a shape ep. Just has a shape. Oh dear. Wait, nope, we're still good. Look at that. Look at that. Isn't it cool? To be honest, it's kind of trippy. Okay, so maybe that's a little much. But I don't know, there's just something kind of entrancing about it, right? Look at the channels individually. So we'll do that. We'll also do cv.im show just the real part, which is part 1. the imaginary part, which is part 2. There we go. So we have imaginary, real, and then the composite. And that's just kind of cool looking. I'm not sure what else to say about it. I'm not sure why there's this box, except that there's a box there and a box here that combine in the color one to make, is that a unit square? No, it's not a unit square. Is that a square that's length root 2 by root 2? I don't know. I'm curious. This must be explored. Import matplotlib.pyplot as plt. So what I'm going to do now is I'm going to graph it on a grid. A proper mathematical grid where I can look at the coordinates and everything. I can't remember how to do that. I can do imshow and just do image and then blt.show. But I need it to be, I need the coordinates to be in the correct place, which I suppose I could do just by changing. Yeah, we'll do that. Copy, paste. That. Oh, make it bigger. Must be bigger. And now this one is red, green, blue. So our colors are different, but the values are all the same. That's fun. And you see this circle? You see this circle here? That's so strange. Very cool. I'm intrigued. -2 to 2. -2 to 2 equals 2. What does it mean? What does this imply? What are the secrets of this Mandelbrot? I don't know that we're discovering anything new. It's just kind of cool. Okay. No, nope. I still want the coordinate system to be correct. Lib. Show set coordinate range. Extent. 0 to 32. Okay. Extent. Extent equals, and this is going to be -2 to 2. -2 to 2. A smarter man would have had it pre-generate it, save it, and then load it back up so that I didn't have to regenerate it every time. But it's fine. Yes. Here we go. So this looks like the square root of 2 over 2. Looks a lot like it, actually. In fact, I know that it is. Do I? Wait a minute. Yes. Yes. Because you see from here to there, that is a square inscribed in a circle. And this circle I know is radius 2 because it's a Mandelbrot and that's what it does. That's so cool. Sorry, I'm nerding out, but it's really nifty. We're going to save that. Mandelbrot. Real, imaginary, magnitude. Cool. But now I want to also save it out of OpenCV because cv.im right. And I want to save. Come back. I gotta hang on. File name Mandelbrot. Full real imaginary magnitude G, and we're going to save img. Cool. Well, I learned something new today. How about you? Okay, done with that. Done with that. That's cool. It'll auto-save it. Yes. Sweet. Alright, well, if you guys have enjoyed that as much as I have, be sure to hit that like button. Hit subscribe, hit the bell to be notified anytime I go live. And I want to start posting videos, but I haven't had a lot of ideas about what I should post. So if you have any suggestions, put them in the comments below. Join my Discord. I check it pretty frequently. But if you have any questions during the week, not during a live stream, pop them in there, and I may put them in my stream notebook, basically. And I'll work some problems here. Otherwise, I may just help you in the chat if it's, imminent. So yeah, we'll talk to you guys next time.